Hello everyone, my name is Greg, and today I would like to walk you through 5 questions from latest AGK exams seen in the last 30 days. Topic for today will be Turbine Engine. Now, question number 1. What information is provided by cockpit indications as regards starting and operating the APU? Fuel flow, air inlet pressure, fault status, or bleed air temperature. So, the APU operation is almost entirely automatic. All we can do as pilots is start it and shut it down. It always operates at 100% N, and we cannot adjust any parameter of operation. On the other hand, the engine has a variety of automatic protections, which will shut down the APU automatically in certain occurrences like low oil pressure, high oil temperature, overspeed, exhaust gas temperature exceedance, or fire warning, but this one only on the ground. Now, for example, on A320, indications for APU we can find on ECAM status display on APU page. We can find there indications regarding APU generator, bleed pressure, N% indication, which also can warn in case of overspeed, APU EGT, fuel low pressure caution message, or for example low oil pressure message. On the overhead panel, we have also a fault indication on the APU master switch. So in our case, the answer number 3, fault status, is a correct one. Now, just to cross-check, let's go through other answers. The first one, fuel flow. Well, since APU operates constantly on 100%, there is no point to have a fuel flow indication because it's a constant known value. Air inlet pressure, we do not have air inlet pressure, and we also don't have a bleed air temperature indication. So answer number 3 is correct. Question number 2. An airplane engine usually has 2 idle settings, flight idle and ground idle. Flight idle corresponds to a higher power setting. This is because engine thrust needs to be readily available upon the go-round. The air is less dense at altitude than on the ground. Less fuel is consumed with flight idle, increasing endurance. Flight idle allows for better altitude loss during descent. Alright, so during flight, the engine operates at higher idle RPM to be able to accelerate quicker to full power. When you start your jet orientation course or MCC, you will see that the turbofan engine accelerates much slower than the propeller engine, where response from more thrust is almost immediate. This feature is especially pronounced at low RPM. Just imagine that on Airbus A320, the spool-up time from idle thrust to full thrust can take up to 8-10 seconds. It is kind of a protection for the engine. It protects from overheating, overfueling, or surging. So from given answers, the correct will be answer number 1. Engine thrust needs to be readily available upon go round. And this is the correct answer. Question number 3. A magnetic plug in an engine's oil system can be used to prevent metallic particles from entering the oil system, collect static electricity, collect carbon found in the oil, or collect ferrous particles. So, the magnetic plug, or as commonly known, a magnetic chip detector, might be installed in the scavenge lines of the oil system. These detectors collect flakes, shreds, or particles of metal, and if any of those are detected, it might be an early indication of impending failure. Upon analysis, technicians can determine from which parts of engine or gearbox these ferrous particles come. So here, the answer number 4 is correct. Now, be careful with the answer number 1, prevent metallic particles from entering the oil system. Remember that a magnetic chip detector is not a filter of any kind, nor a preventive device. It collects metallic particles that are already in the system. These plugs have a pure diagnostic purpose. So answer number 4 is correct. And we are going to question number 4. On a F.A.D.E.C jet engine, the meaning of F.A.D.E.C on a gas turbine engine is, and this is full automated digital engine control, so it's going to be answer number 2. Now, I want to use this question to explain how this system works and what it comprises of. So the key part of the F.A.D.E.C system is the EASA engine electronic controller together with the FMU fuel metering unit. EEC consists of two separate channels, so two separate computers that sense a variety of data for engine itself, but also sense a thrust lever angle, so the power requested by the pilot. The system itself has many features, from sending commands to FMU in order to deliver appropriate amount of fuel to the engine, commanding bleed valve's position, variable inlet guides vanes or the stator vanes position, up to responding to the engine master switches or incorporating engine protections. It is also important to remember that in a F.A.D.E.C system, each EC channel has its own source of electrical power from outside of the aircraft electrical system. So answer number 2 is correct. And going to question number 5. For a gas turbine engine, derated or reduced takeoffs save engine life primarily due to reduced corrosion of the high-pressure turbine blades, reduced low cycle fatigue damage, reduced creep damage due to higher EGT levels during takeoff, or the maximum oil temperature not being exceeded. Alright, so whenever we think about saving engine life, we should think about keeping the engine outside of extreme parameters. Takeoff is one of these phases of flight where we need a lot of thrust. Now, engines are designed to give us necessary performance in very unfavorable conditions like maximum takeoff mass or a high density altitude. But in everyday operations, we do not need this amount of thrust. So, in order to reduce engine stress and increase engine life, we have two methods of reducing takeoff thrust and will still satisfy the performance requirements. The first one is called derated thrust. Pilot can set a predetermined lower maximum thrust for the engine through FMS CDU. The important consideration here is for the method that it can not be override by the thrust lever position alone. So, for example, in case of emergency, the full power of the engine is not available. The second method is a flex thrust, where pilot puts in the FMGS an assumed temperature, which has to be higher than actual one. In very simple words, in order to prevent turbine overheating, the engine software being tricked that the temperature outside is warmer than it actually is, will lower thrust for takeoff. Now, in contrast with the derated method, in the flex thrust, the full power is always available for the pilots by pushing the thrust levers to toggle. And both of these methods reduce engine stress and increase engine life, effectively reducing maintenance costs and cases of fatigue damage at low cycle numbers. So answer number 2, reduce low cycle fatigue damage, will be correct. And that was it for today. I hope you enjoyed and hopefully see you next time.